Okay, we're going to talk about Extrema today. This is a big topic, and I'm going to go through quite quickly. There's a lot of definitions, and there's a couple theorems that we need to know. So I'll go as quickly as I can, but hold on tight. So we have two objectives. The first one is to identify and find absolute and local extrema on an interval. And the second is to apply and state the mean value theorem and Rolle's theorem. First of all, we have to decide what an absolute maximum or minimum is. Okay, so first, a function f has an absolute maximum at a value c. So c is like your input value. If the output values f of c, okay, are bigger than or equal to f of x for all x in a region. Okay, for an absolute maximum is for all x in a domain. So that this right here just says basically we can't have any values bigger than f of c. Okay, f of c is called the maximum value of f on that domain. Likewise, the minimum value is the exact same thing, except we've switched the inequality here. This says we cannot have any values less than that value for all values in that domain. Now, this is or equals to, which means that we can have two values that achieve the minimum or two inputs that achieve the maximum. Okay, but we just can't have they have to be the same minimum or the same maximum. So we say that we achieve a maximum, the output is the maximum that is achieved at an input. Okay, so the maximum at C or the minimum at C is the output. Okay? And collectively, maximum or minimum values are known as extreme values or extrema. Okay? All right. So we can talk about local or relative extrema as well. Okay, so maximum says across, absolute says across the entire domain we have one absolute maximum, but local maximum is also an idea. Okay, where we say again, same basic concept, in an interval containing c, containing an input value, for all values inside that interval, c achieves an output that is a maximum. Okay. Same thing with the local minimum. These should be minimum. Okay, local minimum. Okay, is the exact same thing, so we change the inequality here. Okay, so in all areas near there, it's a maximum. So for instance, this, okay, it's a local maximum here, looks like an absolute minimum here, and a local and also an absolute maximum here. Okay, so local means in the area near. That's a local maximum. That's a local minimum. That's a local maximum. It just so happens that this local maximum is also the absolute maximum. Nothing in the entire domain is higher. This local minimum is a absolute minimum because nothing in the domain is lower. Okay, here's the extreme value theorem. Okay, if f is continuous on a closed interval, then f must attain an absolute maximum value and an absolute minimum value for some numbers c and d in that interval. Now, this only works if we have a closed interval. That means it has to hit an endpoint. It has to hit an endpoint. We can't have something like 1 over x, whereas we approach 0 from 1 over x, it just keeps on going, but it never actually hits x equals 0. That's not going to work. We have to have a closed interval. So for instance, here, we start here at a point, we end at a point. If we start at A and we end at B, then what this says is there must be some value in here that's going to be a minimum and some value that's going to be a maximum. It looks like the minimum is at A and the maximum is just before we get to B. Okay? So Fermat's theorem is it takes this and it goes further and talks about derivatives. Now, Fermat has many theorems. This is known as Fermat's theorem. There's Fermat's last theorem. There's Fermat's little theorem. There's all kinds of Fermat's theorems. This is one of Fermat's theorems. And it says, and we have to be careful about the implication, that if f has a local extreme and the derivative at that point exists, then the derivative is 0. So for instance, here's a local extremum. Okay, a local maximum. If the derivative exists. That's to say it's a smooth, continuous curve, no jagged points, no discontinuities. Here's a local maximum. Then the derivative there, or another way to say it is the slope of the tangent line must be 0. Okay? The slope of the tangent line must be 0 at a maximum or a minimum, a local maximum or a local minimum, is the same thing as saying the derivative is 0. So if f has a maximum, a local maximum, and f is differentiable, okay, that means that f of c exists, f prime c exists, then the derivative equals 0 at that point. That's something that many of you have already observed. It's not really anything terribly new for most of you. But now we're saying it's a theorem. Okay, some consequences, really important consequences. Can we locate extreme values of c by finding c so that f of c equals 0? So if I give you a function, can you absolutely find a maximum value if you know that f prime of c equals 0? Well, that might be true. Let's see here. If I take something like x cubed minus x, if I take the derivative of this and I get 3x squared minus 1, and I find where that equals 0, will that necessarily be a maximum value here? That's an interesting question. Well, let's try this. We know that the one direction is true, that if we have a maximum and it's differentiable, then the derivative is 0. But does it work the other way? Well, let's try a picture here. Okay, I'm going to try x cubed. There's x cubed. And let's take a look and see what happens if we take the derivative. Now the derivative of x cubed is 3x squared. This has a 0, so this is f prime. Again, our function is f of x equals x cubed. Our derivative is 3x squared. 3x squared equals 0 when x equals 0. Okay, so I found a value so that when I plug it in, I get 0. That's the condition I'm concerned about here, right? So the question is that necessarily a maximum or a minimum? Well, let's look. X equals 0 here, nope. That's not a maximum nor a minimum, so the theorem does not work in both directions. If we have a maximum, that maximum has a derivative that is equal to 0 if the function is differentiable at that point. It doesn't work the other way necessarily. Okay, so we have to define a new idea here to deal with this. And our definition is the definition of a critical number. A critical number of a function f is a number such that the derivative evaluated at that point is 0 or the derivative evaluated at that point does not exist. So for instance, if I take x cubed, okay, and I ask, what's a critical number of the function x cubed? Since the derivative evaluated at 0 is 0, okay, then x equals 0 is a critical number. Okay? So it's just a new definition. It's so that we can talk about this class of points. Because notice that if I plug in 0, 0 is not a maximum of f. But it is a special number, so we call it a critical number. Now here's a corollary. If f has a local extrema at c, then c is a critical number of f. Now all that's saying is that now we have a way to talk about these numbers. If I have a critical number, that means the derivative is 0 or the derivative does not exist. So really we can think of it, that's a candidate for an extreme value of f. Okay? In this case, x is a critical number, but it does not happen to be an extrema. Okay? But it is a candidate. It's one of the candidates. Okay. So let's talk about how we find extreme values on a closed interval. The first thing we do is we find all the values of f at the critical numbers of f in a to b. Okay, so we find where the derivative is equal to 0, and we find those values. Then we find the values of the endpoints. Okay? And then we compare, we find the largest values between steps 1 and 2 to figure out where the absolute maximum and minimums are. Okay, let's try an example here. Let's find the absolute maximum and minimum values of the function on this interval from -1/2 to 4. And here's my function. So the first thing we do is we're going to take a derivative, okay, and the derivative is 3x squared minus 6x, just the power rule. Now we try to figure out when is this thing equal to 0. So we set it equal to 0, okay, 3x times x minus 2. You can hear my daughter in the background babbling a little bit. Okay, and that's going to equal 0 when x equals 0 because of the factorization here, or when x equals 2. Okay, so my critical numbers are x equals 0 and x equals 2. Those are critical numbers. Those are candidates for maximums or minimums. All right, those are two candidates. My other candidates are the endpoints -1/2 and 4. So I have 4 candidates for extreme values on this interval. And I plug those 4 numbers in. So if I plug in -1/2, I get an 1/8. If I plug in 0, that's one of my critical numbers, I get 1. If I plug in 2, I get -3. And if I plug in my other endpoint, 4, I get 17. Here's a picture of my graph so you can kind of get a sense of what this might look like. Okay, I've got 0, which is 1. That's this point right here. Let me make it a different color so you can actually see it. Okay, I've got an endpoint, which is -1/2, and that gives me 1/8. So that's right about there. Okay, I've got, let's see, I've got 2, which is -3. That's right there. I've got 17, which is way up here. 4, 17 is up here. So you can see that the function I'm looking at is this function. And I've found those 4 points that I just articulated. 1, 2, 3, 4. Now, my absolute maximum value is this. And my absolute minimum value is this, right? The biggest number out of those 4 is 17. And the smallest number out of those 4 is -3. So absolute minimum, absolute maximum. Now notice this is a relative maximum, pardon me. And this is a relative minimum. So oftentimes when you're doing this, you're going to get values that are relative maximums but not absolute maximums or minimums. All right. So now we want to talk about Rolle's theorem. Rolle's theorem is pretty interesting. Okay. What Rolle's theorem says is kind of similar to the intermediate value theorem, but it's specific to derivatives. So f is a function that satisfies 3 hypotheses. It has to be continuous on a closed interval. It has to be differentiable on an open interval. And the value at the endpoints has to be the same. Okay. What we're going to say then is there's a number in between so that the derivative is 0 between those two values. Okay. So let me give you a basic picture of this. Here's a, f of a, and here is f of b. They have the same height. The function is continuous from here to here. It's differentiable from here to here. So this is a, b, and f of a. Okay, and f of b are the same, right? So the same height. Now, if it's continuous and differential between a and b, that means that it's got to be smooth, and I can't pick up my pen. Okay? So what this means is that there must be a place in between a and b where the tangent line to that graph is 0. In essence, that means that if it went up from a, it must come back down to b, okay, in a smooth way, which means I would have to have a maximum. If it goes down from a, it must at some point go back up to b, so it would have to have a minimum. And we know that the derivative, okay, of a maximum is 0 on a continuous and differentiable function, and the derivative of a minimum is also 0 on a differentiable function. That's the intuition. Okay, so we're going to do an example here. We're going to argue that a ball thrown into the air must at some point attain a velocity of 0. Well, that's not so bad. If I'm standing here and I throw a ball up in the air, it's going to come down. Okay, we know that about gravity. Here's the ground again, right? The ground is the same height the whole time. Okay, so that means that from time A to time B, it went up, it went down. Okay, from maybe 1 second to 2 seconds, it went up and down. Okay, Rolle's theorem says that since it started out at the same height that it ended at, somewhere in between, the derivative of this function was 0. Okay, if this is f, then somewhere in between 1 second and 2 seconds, f prime of whatever that is, call it c, must be 0. But remember, with a physical problem, the derivative of position is the derivative of position is velocity, so that means that somewhere between 1 and 2, by Rolle's theorem, we must have attained a velocity of 0, and that happens at the maximum. Here's another example. This is a pretty cool problem. Prove that x cubed plus x minus 1 has exactly one real root. Okay. First of all, by the intermediate value theorem, f of 0 equals negative 1, f of 1 equals 1. So since this is continuous between 0 and 1, there must be a root between 0 and 1. Okay? Between 0 and 1. Okay, because they cross, we go from negative to positive, so it must cross the x-axis. So we know there's at least one root, and root has no e on the end. Okay, there's at least one root. So now what we do is we assume there are two roots, even though we want to show there's only one. So bear with me for a second. So that means that f of a equals f of b, so f of a is 0, which means that a is a root, and f of b is 0, which means b is a root. First two numbers, a and b, which are different numbers. So they're the same value. The output is the same. So there's a number between a and b, we'll call it number c, so that the derivative equals 0. Okay? If indeed there are two roots, then there must be a place in between those two roots where the derivative is 0. Well, let's look at the derivative. Here's the derivative of the function, 2x squared plus 1. So, by Rolle's theorem, if there are two roots, then there must be a place between those two roots where the derivative is 0. Well, let's look at this. If we solve this for 0, what do we get? We get an imaginary number. So what do we know? We know that since the derivative can never be 0, if we go back, our assumption must have been false. There cannot be two places where we have zeros, where we have roots. So we know there's at least one root by the intermediate value theorem, and we know there cannot be two roots, or by the same argument, there cannot be more roots. So by that argument, we have shown there's exactly one root without ever even finding it. It's pretty interesting. Okay, the last biggie here is something called the mean value theorem. So f is a function that satisfies these hypotheses. It's very similar to Rolle's theorem, except the last condition is a little different. So f is continuous, f is differentiable. There's a number c in the interval so that the derivative at c equals the average rate of change over that interval, equals the slope between that interval. Here's the picture. Okay, and this is another way to write it here. I'm multiplying both sides by b minus a. This looks like a line. It's kind of an interesting point. We'll talk about that later. Okay, basically, here's a, here's f of a comma f of a, here's b comma f of b. And what this is saying here is if I take this green line here, if I pick up the green line, good. If I take this green line, okay, and I run it through a and b, the slope of that is f prime of c. What it's saying is that somewhere between a and b, there's another place where that derivative hits. Aha! Right there, we can see the derivative at this point has the same slope as the average rate of change between a and b. That's the picture we want to keep in mind. Somewhere between these 2 points, the derivative must be the same as the average rate of change. That's the mean value theorem. Okay, we're going to do a proof later on. Here's an example. Okay, so we're going to find a number that satisfies the conclusion of the mean value theorem for this function over the interval 0 to 2. Okay, well here's the picture on the right. Well, we'll get to the picture on the right as we go. Okay. So what it says, we have to have a closed interval, we do, and this function must be defined and continuous on that interval, it is, and it must be differentiable on the open interval, it is. All polynomials are continuously differentiable everywhere. So, the mean value theorem says that if I do f of 2 minus f of 0 divided by 2 minus 0, I'm going to get 3. And what the mean value theorem says is that somewhere between 0 and 2, there's a place where the derivative equals 3. Okay, that's what it says. Alright, so the derivative is 3x plus 3x squared minus 1. So again, the mean value theorem guarantees there's a number between 0 and 2 where 3x squared minus 1 equals 3. Okay, so we just solve for x now. And x equals plus or minus the square root of 4/3. Now, here's the picture. And remember, we only want the value between 0 and 2. So we're actually going to choose the positive. Okay, the mean value theorem says we're looking for a value specifically between the numbers 0 and 2. And 4/3 indeed falls between 0 and 2. Here's the picture again. Here's 0. Here's 2. Now, the scale is not, it's like a quarter for every scale here. So here's 2 right here. Boom. Or half. Okay. And I can see that if I go out to approximately 4/3, which is right, 4/3 is right about there, we can see there's a place where the slope of the tangent line at that point is the same as the slope of the average rate of change over the entire interval. And that's the mean value theorem. Okay, well, I hope you enjoyed my 20-minute lecture today. We will talk about this more coming up.